So we've gone over the exponential function. Now we want to go through and we want to go over the logarithmic function. So if you remember back from college algebra, you guys learned about inverses of each other. So the logarithmic function is just the inverse of the exponential function. So basically, you have an x that's greater than 0, a b that's greater than 0, and this b is the base, just like it is in the exponential function. You don't want that to equal 1 because it's boring. So that is going to be our logarithmic function with base b, and it's denoted by f of x equals log base b of x. So basically the way you can kind of think of this is you have y equals log base b to the x. You can rewrite that as an exponential function. So it's equivalent to x equals b to the y. So I have kind of a cheesy way to kind of remember this. You can think of it as bacon and eggs. So you have log base b of x equals y. This b, just like in the exponential function, is the base. That's the bacon. You have a, which turns into the answer. That's the end. And the y is the exponent. That's the eggs. So it spells out bacon and eggs. So it's kind of a way just to remember how to transform the logarithms into exponential functions. So we're going to go ahead and we're going to evaluate some logarithms by actually rewriting them in exponential form. Because trying to think in your head what an equivalent is more difficult. If you write it in the exponential form, you guys are used to dealing with square roots, cube roots, powers, all that kind of stuff. It's a little bit easier. So we want to rewrite this, so we're going to use that bacon and eggs. So the base, the answer, the exponent. Okay. So x is our base. 64 is the answer. So this will equal 64. And then the 3 is the exponent. So it's the base, the exponent goes up top. So solving this logarithmic equation is the same as solving this exponential, which is a little bit easier. So to get rid of that third power, you take the cube root of 64. So the value of x that satisfies this equation is just 4. Okay. Same thing in the next one, you have log base 16 of x equals 1/2. If you rewrite this, 16 is your base, x is your answer, and the 1/2 is the exponent. So 16 to the 1/2 equals x. 16 to the 1/2 is the same thing as the square root. So really, the value of x that solves this equation is 4. So we have two special types of logarithms. We've got base e, which is our natural base that we learned in the last section. And then you also have base 10. So in these two cases, you have a different form to write that log. So if you're given log base 10, we're often just going to completely ignore it. So if you don't see a log there, it's assuming it's base 10. If you have log base e, it's called the natural base, so this becomes the natural log. So that becomes ln for natural log. So the nice thing, we have a ton of properties with exponents. We have similar types of properties that will stem to the logarithms as a result. So we've got all these kind of criteria. M, N, and B are positive real numbers. B is going to be our base. So again, we don't want it to equal 1. But then P and X can be whatever we want. So we're going to have 7 different properties for logarithms that can help us rewrite things, differentiate, make it a lot cleaner. So the first one is if you're taking a logarithm and you multiply two numbers, you can break multiplication as addition. Or likewise, you can start with addition and condense it to a single log. So you can use either property in either direction. If you have division, it turns into subtraction. So you have log of the numerator minus log of the denominator. The third property is when you have a number to a power, think of this as log base b of m to the third. That's m times m times m. You'd add up that log 3 times using this first property. And then really you get the power will pop out. So our power just pops out front and you get p times log base b of m. Okay? So powers just come out front as multiplication. Fourth one is if you have log base b of the same value as the base, it just equals 1. So those cancel each other out essentially. Likewise, if you have log base b of b to a power, you can pull the p out, but another way to think of this, because the logarithm and the exponential function are inverses, those undo each other and you just get p left over. Okay. The sixth property is if you have log base b of 1, that equals 0. And this stems just from the exponential property, because b is our base, 1 is our answer, and 0 is our exponent. So you can see why that property is true. Okay. And then our last property is called our change of base formula. So if you want to rewrite it, or if you have a calculator that doesn't allow you to evaluate with bases other than ln or 10, you can rewrite it as log of m over log of the base, or natural log of m over natural log of the base. So this property here is called our change of base formula. So it can be helpful if you're evaluating things. It can be helpful as well for taking derivatives, but we're going to use it mostly to help us with finding out what the derivative of other natural log functions are. So let's work through an example. We're going to be given that log base b of 3 is 7 and log base b of 5 is 9. So we have no idea what the base is. If you were to try to solve this, it's not going to work out nicely. You'd get some approximation. But by knowing these two things, we're going to evaluate two different logarithms exactly. So we want to first evaluate log base b of 1 over 5. So what we need to do is we need to somehow introduce these logarithms in there if possible. It might not be possible. But we have division. One nice thing we can do is break that apart as subtraction. So this is log base b of 1 minus log base b of 5. Okay? So because of that, log base b of 1 just becomes 0. And we know what log base b of 5 is. So this is equal to 0. Log base b of 5 is 9. So we get 0 minus 9. So this just equals negative 9. Okay? So we want to do the same type of thing for the next one. I don't know about 75, but maybe I could break this down to have a 3 or a 5 in there. So the first thing we can notice is 75. You can write as 3 times 25. Okay. And now with that multiplication, you can break it apart as addition. So it's log base b of 3 plus log base b of 25. And we know what log base b of 3 is. That's going to equal 7. And 25 we can even rewrite dealing with 5s. So that's 5 squared. So one of our properties is the power comes out. So it's 2 times log base b of 5. And log base b of 5 is 9. So this becomes 7 plus 2 times 9. So that's 18 plus 7. This ends up equaling 25. Okay. So our graphs of the logarithmic function are going to vary based on the value of b. The exponential function, we had two different graphs depending on if the base was bigger than 1 or if it was between 0 and 1. Same type of thing happens here. So for this first one, if the base is greater than 1, here is our exponential function. As x gets bigger and bigger, it goes off to infinity. The nice thing is, because again, these are inverses of each other, you can flip that over the graph y equals x, and the logarithmic function goes from negative infinity and it keeps increasing. So one thing we have to be careful about, what's inside the logarithm always has to be positive. That domain requires that your x is greater than 0. Same thing if we go to look at the base being between 0 and 1. Here's the graph of y equals b to the x, so that's our exponential function. Our logarithmic function is its inverse. So you get this other graph, which is really a reflection of the other base. So both of these are going to have the same x-intercept. So they intercept the x-axis at 1, 0. The domain is from negative infinity to positive infinity. Or sorry, the range is from negative infinity to positive infinity, and the domain is from 0 to infinity, because that's the reverse of that exponential function. So now we're going to utilize the fact that these two functions are inverses and the way we can rewrite the logarithms to find the derivative of the natural log function. So we went through that before by going through the formal definition and showing you where the derivative or where the number e is defined from. We can use implicit differentiation again to help us with finding the derivative of y equals natural log of x. So the first thing is we've got this function. We can rewrite it. So ln is the same thing as natural log. Using that base answer exponent, the f of x is our exponent, e is our base, and the answer is x. So we can rewrite this as e to the f of x equals x. So this is exactly that implicit function. We're going to differentiate with respect to x. So we differentiate both sides, and then over here, we've got to use chain rule to take the derivative of e to the f of x. So you get e to the f of x, but chain rule tells you you have to multiply by the derivative, okay? So this piece here comes from chain rule. And then on the right-hand side, the derivative of just x is 1. Okay. So what that gives us is e to the f of x, which is what we have right here. We can replace by x because they're exactly the same. So x times the derivative is equal to 1. So if you solve for the derivative, f prime is equal to 1 over x. So what this tells us is the derivative with respect to x of the natural log function is 1 over x. And if you want to do this more generally, if you have a function inside, you have to apply that chain rule. So you get 1 over the function. Chain rule tells you multiply by the derivative as well. So this is our most general form for the derivative of the natural log function. Okay? So let's go ahead and get some practice differentiating these, combining it with the stuff we already know. So the first one we're going to look at is negative 9 times the natural log of x. So we just go ahead and differentiate. The constant just stays detached, and the derivative of natural log of x is 1 over x. So this derivative is just negative 9 divided by x. Okay. For the next one, we've got g of x equals x to the 5th times natural log of 3x. We've got to use product rule on this. So we get g prime of x is the first. And then we want to times it by the derivative of the second. So before I go ahead and take the derivative, I'm just going to kind of sketch in what it is. Then we add the second times the derivative of the first. So the derivative of x to the 5th. Right. Now we've got to be careful. We don't have just x inside this natural log. So we get x to the 5th. Derivative of natural log of 3x is you get 1 over this function. But chain rule tells you you've got to multiply by the derivative of this because it's no longer just x. And then in the second one, you get natural log of 3x. The derivative of x to the 5th is just power rule, so it's 5x to the 4th. Okay. So one more step really, we get x to the 5th, 1 over 3x. Derivative of 3x is just 3. And then we add natural log of 3x times 5x to the 4th. So we get some cancellations. The 3's do cancel. One of the x's cancels, and you're left with 4 of them. So you can do a little bit of simplification. This becomes x to the 4th plus 5x to the 4th times the natural log of 3x. And you can leave it just like that. Now for our next one, we've got the natural log of x squared minus 7 divided by x. You absolutely could use chain rule and quotient rule. So you would get 1 over this function, and then chain rule, you have to multiply by the derivative. But one of the really nice things is we can use properties of logs to help us out. So you've got division of two things, split it as subtraction. So you get natural log of the numerator, which is x squared minus 7, minus natural log of the denominator. So now when we go to take the derivative, you can just differentiate each separately. So derivative of the natural log is 1 over that function, and then chain rule again, multiply by the derivative of that function. And then 1 over x is really, or natural log of x is really nice because its derivative is just 1 over x. So one more step, derivative of x squared minus 7 is just 2x because the constant would be 0. So we get 2x over x squared minus 7 minus 1 over x. Okay. So if you can use properties of logarithms, go right ahead, make it a little bit simpler. Don't have to deal with as muddled, because if you did go through using quotient rule after using chain rule, you're going to get a really complicated looking answer. Okay. So let's do one more just to get some practice. We've got the natural log of 8x. So we've got a function inside of a function, and that is inside of another function. So we're going to really have to apply two chain rules here. So remember, we want to work from the outside in. The outermost function is that first natural log. So you get 1 over the inside function. So you get 1 over the natural log of 8x. And now chain rule tells you you've got to multiply by the derivative of the inside function. So now we go through and take the derivative of this. You get 1 over the inside function, but chain rule again, because the inside's not just x, you have to multiply by the derivative of the inside. Okay? So I'd recommend kind of taking it step by step. Don't immediately try to jump into it because it's very likely you're going to miss a component and then have some issues. So one more derivative we have to take, and then we'll clean up a little if it's simple. The derivative of 8x is just 8. So we have a tiny bit of cancellation. The 8's disappear. And then cleaning it up, you just get 1 over x times the natural log of 8x. So let's do one more example. Let's make it a more realistic one. So we're told the profit in thousands of dollars from a sale of X 1,000 candles can be estimated by this profit function. So P of x is 2x minus 0.3x ln of x. So what we want to do is we want to find the marginal profit. And remember, anytime you hear just marginal, it wants you to find the derivative. So we need to find the derivative of the profit function. So we take the derivative separately. Derivative of 2x is 2. This minus sign is going to be attached to everything. So you can do this in one of two ways. You can just apply the product rule to this and then distribute the minus afterwards. Or you can treat this negative 0.3x as your first function. And then you can make the natural log your second function. So either one's going to work. If you look in the notes that I actually posted, I went through distributing that minus sign. I'm going to go through and consider it a different way here for you. So we have to apply product rule. We get the first function. So that's the negative 0.3x times the derivative of the second function. Then we add the second function times the derivative of the first function, which is that negative 0.3x. Okay. So the derivative of the natural log is 1 over x, and the plus and minus becomes just a minus. So you get 0.3x times 1 over x. And then the derivative of negative 0.3x is just the constant. So you get minus 0.3 times ln of x. So a little bit of cancellation. Our x's disappear. So this is equal to 2 minus 0.3 minus 0.3 ln of x. So we can simplify a tiny bit. The marginal profit is 1.7 minus 0.3 natural log of x. So the second part we want to answer is how many thousands of candles should this company sell to maximize their profit? So remember, to maximize, you want to find those critical numbers, and then you want to apply that first derivative test to see if it's a max or if it's a min. So first things first, we're going to find the critical numbers. So that would be where this thing is equal to 0 or where it's undefined. It's technically undefined at 0 because the natural log function has a vertical asymptote. But we need 1.7 minus 0.3 ln of x to equal 0. So if you add the 0.3 ln of x to both sides, we get 1.7 equals 0.3 natural log of x. Then go ahead and divide by 0.3. You're going to get a rough approximation if you plug it into your calculator immediately. So I'm just going to leave it as is. The natural log of x is equal to 1.7 divided by 0.3. So if you rewrite this or take e to both sides, because the e and natural logs undo each other, you get x is equal to e to the 1.7 divided by 0.3. And now if you plug that into your calculator, these are in thousands of units. So 289.069 thousand candles they would have to sell. So this is your only real critical number. You need to see, is it a max? Okay. So we need to test that yes, this makes our profit function a maximum. So you really don't care what happens below 0, although this is where a vertical asymptote occurs. If you plug in, say, 1 into this function, 1.7 minus 0.3, natural log of 1. Natural log of 1 is 0, so you get something positive. So that tells you the derivative is increasing. And if you go ahead and you test anything over here, you're going to get the derivative is negative, so it's decreasing. So yes, it is a max. Okay. So what that means is they should sell 289.069 thousands of candles to maximize profit. Okay. So these types of functions appear a lot in realistic scenarios. So our next section is going to kind of go over some of those applications.